So here we have the last example in the section on beams. One more example on cantilevers. So just a quick recap on cantilevers. We're always going to have them fixed on the left and free on the right. And we'll need, because we're going to have 4 antiderivatives, we're going to have 4 boundary conditions. So our boundary conditions are as follows. Reflection at 0 is 0. This is going to give you C2 equals 0. This is also going to be the case for simply supported and fixed ends. Now the other thing, because of the wall, if it was simply supported on the left, it would just look like that. You have a negative slope, but if it's fixed on the left, the wall or whatever will have it coming out straight. So here, the slope at 0 is equal to 0, and if you implement that, which we'll talk about again in the summary later on, C1 will be 0, and that will also be the case for fixed ends. C1 is proportional to its EI times the slope at 0, and therefore for simply supported, C1 is not 0, it's actually negative slope. Now there's 2 ways of kind of dealing with this boundary condition. No, there isn't. So the first is that the reaction here is the sum of the loads. So all the load coming down must be balanced by those coming up, so the RA is the sum of the loads, that's one. And the other one here is that there's nothing causing any bending at the end. So the bending moment at the end of the beam is 0. I am not too sure what this CL stands for. Oh, this is cantilever only. Okay. Alright, off we go. We'll go off and solve this. So we did one example in class, and now we will look at a second example. So the best thing with all these beams is to draw a picture. We've got a UDL between 1 and 3 and a point load at 5. So we'll draw a picture. I will draw the wall so that I actually see the boundary condition. I'll give it a bit of bend or deflection on it there. Something like that. So we do know in particular that the beam comes straight out of the wall. So the slope is 0 is 0. That gives you C1 is equal to 0. Okay. We've got a UDL between 1 and 3. And it has a strength of 48, so 48 kilonewtons per meter, and we have a point load at 5 of magnitude 18. And so what I'll do is I'll write down the load per unit length. So the UDL, it gets turned on at 1, so you have 45, turn it on with a U, x minus 1, and turn it off with a minus 48, u of x minus 3. And I also have that point load knocking around plus 18 delta x minus 5. And if you look at the equation on the previous page, a couple of pages back, page 96, EI times the 4th derivative of the deflection is minus this. So this was plus minus plus, it's minus, so it becomes minus plus minus. Plus minus plus, minus plus minus, minus plus minus. Off we go, and to differentiate 4 times, remember each time to pick up an antiderivative, pick up a constant. So we go from, fix the constant here, EI. Antiderivative of the 4th derivative is the 3rd derivative. Fix the minus 48. Antiderivative of u is square bracket. Plus fix the constant 48. Antiderivative of u is square bracket. And careful, the antiderivative of delta is u. We pick up a constant here, which we should know this first one is RA. Now we go again, we want to differentiate a second time. So I have EI times the 2nd derivative, so fix the constant anti-differentiate. I'm going to go slightly faster than I might in class. So if I fix the minus 48, the antiderivative square bracket is square bracket over 2. I'll have minus 48 over 2, which is minus 24.
square bracket squared. Similarly here, that 24, square bracket squared. And then the antiderivative of u is square bracket. And the antiderivative of RA is RAX, and we pick up a second constant of integration, which is MA, which is definitely not equal to 0 here, because the wall, we simply spotted MA be 0, but the wall is exerting a bending, so MA is not 0. Now we anti-differentiate again. So fix the constant EI, antiderivative second derivative is the first derivative. Now here you get square bracket squared over 3, so you'll have minus 24 over 3, which is minus 8. Square bracket cubed. This will be cubed over 3, so this will also give you 8. And antiderivative of bracket is bracket squared over 2, so you have minus 18 over 2, which is minus 9. Fix the RA, the antiderivative of x is x squared over 2. Antiderivative of MA is MAX, and you pick up another constant C1, which is the proportion to the slope is 0, so this is certainly going to equal 0. Once more. Fix the constant EI, antiderivative y dashed is y of x. Now you're going to bracket to the power of 4 over 4, so the minus 8 over 4 will be minus 2. And now this will be cubed over 3, so the minus 9 over 3 will be minus 3. And be careful here, you're going to have... Can you even see that? Sorry. Apologies if you couldn't see it. We go again, RA over 2, fix that constant. And the antiderivative of x squared is x cubed over 3. Now fix the constant MA, antiderivative of x is x squared over 2. Antiderivative of C1 is C1x. And pick up the final constant, C2. Now our job is to find all the constants. Now some of them shouldn't be too bad. Because it's fixed on the left, C2 is equal to 0 because the deflection on the left is 0. So that will be the case all the time, simply support of n fixed ends. C1 is equal to 0 because the slope is equal to 0 on the left. This will be the case for fixed ends but not simply supported. And RA is equal to the sum of the loads. Now if you go back and look at the load, this is per meter. So you've got 2 meters, so it's 48 by 2, so you have 96 kilonewtons there, and another 18 there. Add them together, you get 114. And the last thing to find is MA. Now, the way you find MA is we know that the we know that the bending moment at the end of the beam is equal to 0. There's no bending moment at the end of the beam. And M of x is equal to EI times the second derivative. Now this particular fact may not be in the question. It'll probably actually be in the question above, but it's certainly at the back of the exam paper. So now this is not an implication and I'm worrying on with that. It's just a fact. And so if m of 6 is, if this is equal to 0 and x equals 6, this isn't equal to 0, this must also equal to 0 and x equals 6. To be honest, I really should have EI times y double dash just 6, because that would be the same as m of 6. So m of 6 is actually EI times, or rather m of x is EI times the second derivative. So I come back up here a second, and this here is m of x. And as I said, this little equation would be on the paper. Right, so here, I'm going to substitute in x equals 6 into this, and I get out 0. Hopefully the space is with me. So m of 6 is the same as this, as we said, is minus 24 square bracket 6 minus 1 squared plus 24 square bracket 6 minus 3 squared minus 18 square bracket 6 minus 5 plus RA, which I actually know is 114, times X, which is 6 plus MA, and this is equal to 0. So this is the bending moment at 6. So substitute in my 6's.
And we know from the boundary conditions that the left arm of the cantilever, or should I say the right of it, there's no bending there. Now if there's a point load there is, but we're never going to throw that at you. So this is the bending moment at any point x. Substitute in x equals 6, you get this. So this is just a little equation MA, which we should be able to solve fairly easily. So here we have, probably go to the calculator. The first thing is minus 24 by 5 squared, which is minus 24 by 25. I'll just do the lot of it. This is 24 by 3 squared. This is minus 18 by 1. And this is 114 by 6. End up with 282 plus MA equal to 0. And you want to be careful, MA should always be negative here because, well, I won't go into that, I can't confuse myself. So we'll take away 282 from both sides. MA is equal to minus 282. And what you can do then is, if you go back to this, you can substitute in your values. RA is equal to 114, so you got 114 divided by 2, which I believe is something like 57. Divided by 3 is 27, so we should see 27x cubed. Oh crap, no. 57 divided by 3 is 19, so you get a 19x cubed. And then MA divided by 2, minus 282 divided by 2, minus 141. And then to get rid of the EI, you divide both sides by EI. So you get this. This is the deflection at any point, and the question that you will be asked is find the maximum deflection on the cantilever, and the maximum deflection is always at the end of the beam, in this case at x equals 6. So Y max, maximum deflection, is equal to the deflection at 6. So I'll just throw a red in there. It'll be in terms of E and I. If you make E and I larger, the maximum deflection gets smaller. So 1 over EI minus twice square bracket 6 minus 1 to the power of 4 plus 2 square bracket 6 minus 3 to the power of 4 minus 3 square bracket 6 minus 5 cubed plus 19 times 6 cubed minus 141 times 6 squared. So this is the deflection at any point. We're interested in the maximum deflection that's at the end at x equals 6. 6, 6, 6, 6, 6. Should be a question of just banging it into the calculator, because these are square brackets of positive things, they're just themselves. So what do you get? Minus 2 by 5 to the 4, plus 2 by 3 to the 4, minus 3 by 1, and plus 19 by 6 cubed, minus 141 by 6 squared. And your answer should be negative. So I'm getting 1 over EI times minus 2063, which is equal to minus 2063 over EI. EI is of the order of about 100, so this is about 20 millimeters, it's about 2 centimeters, which isn't that much.